Yeah, and here we are. Hey,
Hey, Luca.
Thomas, how are
How are
you?
you?
I'm
Good.
tethered. I'm tethered again because when you leave headphones not in your backpack, or sometimes even in your backpack in my house, but outside is the kind of the guaranteed is that someone will use them and just use them until they're dead. And in the end, instead of saying, "Yeah, let me charge them," they will just put them back. Yeah, it's the laziest thing ever. Anyway, that's my story. What's yours?
Yeah, I'm just using a thing that's like a conference mic.
Ah, fancy. Yeah, yeah, no.
But yeah,
I'm
uh, the, the other thing is that today is a pretty hot day. I think it's 30 centigrade for the first time.
Oh,
And
wow.
uh, and so when it was 5 minutes ago, I got the drink. So I thought, well, during the podcast, but yeah, it's all gone.
Yes.
Um, but yeah, other than that, it's pretty good. And
Nice.
this week I found a found an old and nasty bug in the Python interpreter because I've been looking at the prologues, and so that's good because it will probably run much better and not
Yeah.
like crash every thousandth time. And yeah, so that's what's going on.
Yeah, what are you like? I know you're doing work in the interpreter, and to unblock a kind of two, three use cases that we have in mind. So
Yeah. So
that's
what we
exciting.
want to do is we want to have a more modular view of the prologues. Like we talked a lot about how we want to have transforms and things like that. But now, if you could apply the machinery that we have, not like on the outside during the thing that is called, but also on the inside, that opens a lot of possibilities from more aggressive caching in order to reduce the interpretation time to having calling Thunder modules in Thunder optimized code. And that would be interesting for training runs and stuff like that.
Yeah. Yeah, very
Oh yeah,
nice.
but
Good, good.
it's still some work to do. But it's good if you can fix some of the bugs that have been like every now and then the CI would fail inexplicably, and
Hmm.
now we know why.
That's good. That's good. In other news, I was in London yesterday and the day before. We had a great Lightning AI agents hands-on session. Um, that was pretty interesting because I finally got into agents and I did it through how the sausage is made again, yet again. So built a very 200 line agents library that made it very clear what is craft, like what is stuff on top, stuffing, and what is the core. And yeah, it was pretty interesting, and people hung out for a long time. So that was fun.
Also,
But now we're gonna talk about not really prompting, but like fine tuning. And there's a thing that it's called LoRa that is really interesting. That has been dominating since basically since Stable Diffusion and since the first models came out. But I think it started with Stable Diffusion and people adapting Stable Diffusion,
well,
or even before.
I think it started even earlier, but
Okay.
with the bird type models, and
Ah, I see. I didn't realize that. Yeah, yeah,
yeah,
it's very likely. Yeah, but actually, there are certain things that are at the boundary of what a compiler should do, and there are certain things that when we all say the how and the what. So the what and the how is like the transform, and the what is the model definition. And there's things that are kind of in between, where it's a what, but it's also a bit of a how. And I think LoRa is one of these things. So let
we
me share my screen real quick, and we'll go through a very quick scribbling as usual because we like it. Um, All right, so we have our model, transformer model. Let's say you have an attention block, you have an MLP, and you have many of these, blah, blah, blah. And of course, I'm disregarding a lot of them, but the juice is, and of course, you have the residual streams. And when you fine tune, you can do full fine tuning. And the full fine tuning is you adapt every single one of the weights to change to your fine tuned data. Of course, on a like 20 billion model, billion parameter model, or whatever it is, 32, it's a lot of parameters. A lot of parameters also means you need to use enough data to change them. Otherwise, the change will be kind of not very substantial. And so, in order for you to adapt the model more cheaply on a smaller amount of data, you can use something called low rank. There are many techniques to do that. Like it falls under parameter efficient fine tuning (PEFT), which is also a library from Hugging Face, but the name is the name of the technique. So parameter efficient fine tuning is fine tuning without changing everything, or changing a subset of the weights. And so you have low rank approximation, in short LoRa. What does this do? Instead of like freezing some parameters and not others, it says, okay, let's freeze everything from the base model, and let's basically add a matrix in parallel to whatever you want to adopt. You can choose only the MLP, only the K and V, only, or all of them. But for each linear layer, essentially, it will tell you, okay, let's create another matrix. But instead of creating a full matrix with the same number of parameters, let's create a matrix out of outer product between, or a matrix multiplication between a very, two very thin matrices. And so if you express one matrix as a product of this very skinny matrix and this very short matrix, and you can imagine that you can make them as skinny and as short as you want, by multiplying this, doing matrix multiplication between these two, you kind of recover the dimension of the full matrix, but the rank of the matrix that you obtain is much lower, in the sense that rank is the number of linearly independent rows and columns. And so the rank of this matrix will be, resulting from this operation, will be much lower. You still get a matrix that, yep.
It will be like the size of the matrix or the inner dimension there, right?
Yeah, exactly. Yeah, that would be the rank. And so you still have something that is compatible with respect to the sizes to the matrix you need to add it to, but it ultimately made of a lot fewer parameters, which are the parameters that fit here. And
fewer trainable parameters, right?
Yeah, exactly. Fewer trainable parameters, because you will obtain this from this one, you will obtain from this one, and this one is like the generating original matrices and the set of parameters. So you can actually fine tune using a small subset of the full number of parameters. You're not fine tuning the parameter in the model. You're fine tuning something that you can overlay on top of your model that is generated by a very small set of parameters. So as you can imagine, if you have a linear here and you want to do a LoRa thing, say you have your activations and activations in output, and you have your matrix here, and now you're saying, okay, let's set as an input to this other matrix the same vector, right? So it's like that. And then you come out and then you add, right? You do, or you can also just add the two. It's a linear operation. So you can just superimpose and merge the two one on top of the other. And this looks like a change in the computation, right? If you could take this linear and replace it with something else, which is the combined linear or even the disgregated linear, and you augment your computation replacing this unit with this unit that has the frozen parameters, which are here, and the unfrozen parameters that are here, or actually that are here, and that you obtain the full matrix through an operation. Then you could do it with a transform, in theory, right? So you could say, okay, let's now keep the model as it is and get to a path formulation through a transform that I can add to Thunder to make it happen. So that's why it's kind of at the boundary, I think, of what you want to do with a compiler, because arguably you're changing the what, not just the how. So it's kind of there. You need to have the sensibility, I think, not to take it too far. But for this kind of thing, if you think about it, like if you do a quantized computation, it's not so different, right? Because we are also changing a bit of the what, and you're computing something that's different, but kind of the same.
And really, you do the training, right? And you train the same model, and after the training, as you explained, you would fold back the addition to the weights into the weights, and you would have the same model, right?
Yeah, exactly. So it's a procedure called, usually it's merging the LoRa layers back into the model, which basically means you obtain the matrix from the low rank, and then you just add the weights on top of each other, and you're back with the same model. Yeah. Just like when you're training quantized and you want to recover your full precision weights, basically you're kind of doing an operation with the quantized weights, with the scaling factors, and you're kind of recovering. So it's very, very close, but it gets a bit more on the how, on the what of the computation is. Anyway, so Thomas today will show us how to do it.
But so the nice thing here is that with the change of the parameters that our model has, you also have the state dict thing, and then folding it back, you could, but actually it's not yet in Thunder, you could implement this using these composable state dict transforms. So that is another, why you might want to do it with a compiler after all.
Yeah, in fact, if you have a very chunky model and you have this very lightweight LoRa layer in terms of quantity of parameters, you could serve many of them. There are examples out in the wild where, you can have many very lightweight LoRa layers, and then you just load one model on the GPU, and you can swap these in and out. And so it also makes sense to do the state dict and keep them separate to make it easier to just store these once, even in a model store, or even in your image that you need to serve this model from, and several gigabytes. You don't have to download them for each LoRa fine tune. You just get the fine tune that you want, and you serve it in a disgregated fashion if you want, and so on. Yeah, great. Anyway, let's stop babbling here and get to the thing. So today we're going to see LoRa as a transform.
Yeah, so we do have LoRa as a transform actually in Thunder, and one interesting bit of trivia here is that it was, I think, one of the larger contributions of our first open source contributor, and that was last year, and this year she's one of our colleagues, right?
Exactly. Awesome. That's a very nice story. Yeah, I just met her. I was with her yesterday in London. It was a lot of fun.
And so I copied it from the LoRa file in Thunder into a notebook just to show it here. And this is the transform. It does a number of things, and we'll briefly go over it. And I also copied the test that we have for it. And so currently with the code that is in Thunder, it's all good. And we will we will change things, and hopefully we get all good afterwards too. But so let's briefly look at what this does. It's a bit of code, but so the transform, it has a transform module that needs to find the linear layers that we want. There's a small twist if you have shared parameters. And then this is transforming the module. The main thing is adding these LoRa A and B slim matrices.
Yep.
And then for the state dict, we do this, we also add the matrices, and we don't transform it back yet, but so it is. And then there's the transform traces, and this is like the core of the thing that we've been discussing all the time. The other parts are important too. But so the first thing, and this is not as elegant as it could be, is that it adds the code to extract the new parameters from the module to the prologue. And that's not the part we want to look at today. But the part we want to look at today is what it does with the computation trace. And this has several parts. The first thing is, and this again should be easier than it is currently, but the first part is that we add the new parameters as arguments to the computation trace. Recall that this is like how it goes.
It's functional. It needs
It's
to be functional, so more
so
parameters, more inputs. Yep.
right. And so for each of these, we need to add one of these unpack trivial, which basically just is a producer for whatever symbol. And so we need to add those. And then comes the transform itself. And what it does, it looks for the Thunder torch linear. And then the argument names that are found from the prologue. And if it's one of the things we want to replace, it does this thing, and we will look at it a bit. And so I might delete this and this because we don't really need it. But this is basically the computation. You first have a dropout thing. Then you have the LoRa A and B weights for technical reasons because we want to be compatible with the LitGPT LoRa. We transpose the weights, and then we run our input, which has gone through the dropout. We ran that through the first matmul, the second matmul. Then we scale it by a scaling factor, which is a hyperparameter, if you want, of the LoRa. And then we compute the original path, which involved using a linear. And then we need to add those two together. And you see that this is like a funny thing because it now needs to specify the output, which was the original proxy output.
Mm-hmm. And so it goes back into writing into whatever was the output originally.
Yeah. And this doesn't seem as nice as we wanted. And what's more, that if you have something that actually changes the outputs, this gets even more tricky. So, for example, when you do sharding, there are even more things that kind of can happen. Then there's a technical thing because we have a thing where we keep track of the arguments of a function. For technical reasons, we add them to the return statement, and we need to update that too for the new parameters. And so this is like a for loop, and then afterwards we have added the bound symbols here manually. And we wanted to have some automation that eliminates some of the foot traps. And this is what we did here in this. We added a new class called the trace substitution processor. And the good thing is that we don't need to read through the entire class, but there's an example here that just reruns all the symbols. And what it does is for each, it goes through the trace. The loop has been like subsumed into the class. And for each, it has this process bsym function that it calls into, and then this can do its thing, and it has several methods to go with. So you can add process bound symbols and set the result. Or you can just say, yeah, go take this from a function. And this seems like a neat thing to do. And so this would be the first thing we do here, is that we define a function that basically does these things. And I cheat a little bit, and I have prepared this function. So let me see here. But it's not.
And does that include the addition, the final addition to the output?
Yeah. So this is like LoRa linear compute. It does the dropout, then the
super clean.
2 manifolds, the mole, the linear, and then it adds the two together and just returns the result. And of course, this is like a nice thing. I'm always saying like a mathematician would write it. And now we need to have a way to put this into the computation trace. And this we do by defining one of these processors. Let's call it a LoRa processor. And to make my life easy, I will make it a local class. And so the first thing I need to do is initialize the thing. And this goes like this. I define the LoRa processor, and I should probably use imports to do this, but it gets the substitution processor. And then we have the new compute inputs that we just take from the outer thing. And then we have the transform that we want to hold on to, that we pass on to the instantiation. Okay, so this is the easy part. And now we need to have a replacement for these things here below. And so the first thing we have is handling the unpacked trivial. And basically what we did here is we skipped the old ones. And we can do this again. And so we just add the process bound symbols, and we set the result. And I actually stole that from the rerun processor that we had before.
Yeah.
Okay. And so the next thing would be to, oh, no, I deleted the new bindings. Okay, so here are the new bindings. And so if we're here, we found the first bound symbol that is not unpacked trivial. So if we still have the self.new compute inputs.
Yeah, but let's maybe remind what unpacked trivial is. It's from the computation tray.
It's like taking the argument and just producing a producer. It's like a Python no-op, but it just, in order to have sources for all producers for all values that are in a trace, we add these. And so we add new ones here. And what we do is basically we say, if we have these still, then we add process bsyms and just pass this list that we had before too. And here we want to use our own value for it in this for loop. Let me.
Yeah, that's good.
And then, of course, once we've done it, we don't want.
Oh, there's an indentation issue. Yeah. Okay. It's a square bracket. Yeah.
Like that. Okay. And so then we want to clear the compute inputs, right? And so this took part of this. And now I'm not doing the return because I want to do this when I have a new bound symbol, and I still need to process the new bound symbol, right? And so, of course, the other case that we need to cover is that this is actually, and we have made progress, so we don't need this anymore. But now we're here, and we need to process the linear, and of course we have a new function that does all this. And so what we can do is we can just take this and fix the indentation, and then we just need to call the function that we had, and we do this with this thing we saw, take the bound symbols from the function call. And let me cheat here again because I wanted to not produce that many typos. And basically, we just say, well, take the bound symbols by running this function here with the arguments that follow, and then just take the output of that in place of the old bound symbol output. And so this is that, and it's arguably this part is a bit cleaner. And of course, it also takes care of this replacing outputs and things, right?
Yeah.
Okay. And so the next thing is that we need to cover the Python return. And so the easiest thing to do here is that we say, yeah, add this again here from the function call. And so we just call the prim Python return with the new return dict argument. And that's all there is to this case. And we can just do return here. And now it's the default case. And so the thing we need to do here is just rerun the symbol. And we need to, unfortunately, do a bit of trickery with the inputs sometimes. And so I will do this here. Maybe we should find a better way to do it down the road. But so this is the new thing. And now I need to, of course, instantiate the processor and call it. So the new computation trace is this LoRa processor. Oh, okay. So this is the LoRa processor, and I need to pass the transform, which is self, and the new computation trace as arguments. And yeah, that is this, and I need to call it. And so because we also grew this recently, and I want to be tidy here, I will do this. I will check that we did this well. And so from Thunder, dev utils, and of course, when I submit this PR, and I will make it into a PR after the podcast, then I will take this out again, but we can check the new computation trace with this trace checker that checks that all the proxies are of the right kind, and also that that if there are two things with the same name, that it's actually the very same thing. Of course, we want to put this into the traces themselves, that they are a bit more picky, but so far we haven't. And now I've managed to put in an error. Okay, so trace has no return, so no output. That's not good. So why does it not have a return? Self add psims from function. this should be, did I mess up? No. So when does this happen actually?
Sorry, can you scroll up in
Yeah.
the code? In the code, maybe it's not entering the condition because oh no, it is bsim sim. I thought it was just bsim.
Uh,
Let's check that it enters that condition though. No?
let's check what again?
Yeah, if it enters in the processor, if it goes through the conditions with
Well,
the return.
but where does it actually happen? So we call it with the new computation trace. And the new computation trace doesn't have, oh yeah, I know what's happening. So where does it start? There's this that cleans all the bound symbols, and we want to remove that too.
Okay.
It actually produced the empty trace.
Yeah.
Once we don't do foolish things from the copy pasting or now the not deleting, but we wanted to show it a bit incrementally. And
Yep.
now everything looks like just like the old thing.
Yeah, let's walk through the example, the test, just to see what it does.
Okay, so we have a model that is our full rank model, and it's a 2-layer MLP, nothing too
Yep.
crazy. And then we have a comparison model that uses the LitGPT LoRa linear, and so it does this. And what we do is we compare this LoRa transform module, or we instantiate the LoRa transform, apply it here in thunder.jit. We just add the transform. And then we compare this to to running the original model. So it just thunderjits the original model, which is
the LoRa one.
No, it's the non-LoRa one. So this needs
the non-LoRa one
before you train things.
Yeah.
But then we also compare to the original module when we load the state dict into the transform module, which is the LitGPT LoRa one. And so we compare it to the out, and we take the state dict with a few renamings from the thunderjitted model. And so this has to be the same too. And then we check that the flat arcs are like the right thing.
Nice. So basically summarizing, we have written a piece of PEFT as a transform, which is pretty cool. And the loading, we could, and also the saving the state dict could be done the same way eventually. So it kind of opens up quite a few possibilities. And what about distributed? Like once we have this, then the trace has its layer, so it's just a trace. That doesn't. It's not special at that point. It's just yet another trace, right? So you could FSTP it, and you could do whatever you do. So the LoRa layer doesn't need to know how to distribute itself because now it's just a simple computation.
Yeah.
Yeah, that's pretty cool. Yeah, it makes you think about like what other things you can do to push the boundaries like of the how into the transform. It's pretty interesting, yes. Because now you could even, I don't know, you start thinking like we basically took a computation expressed just as a computation. So we expressed it in a functional way, right? And just thinking out loud, we expressed the
LoRa
extra, the LoRa part using functional from Torch, right? Yeah. Of course, it can't be, well, it could be a module, not right now. I mean, maybe one day. Maybe with the
Well,
work you're doing actually on the
well,
product.
so oh yeah, I didn't share it again, right? So but so one thing that will be interesting is like how do you get the thing? Right now we just had the linear that we replaced, but in the
Hmm.
end we might want to find something for like larger blocks of code, so we need
Right,
some
right.
pattern matching or something.
Yeah,
But
pattern matching is something we've never, like we kind of started. There's some pattern matching in the repo, but it's not there essentially. And it's one of these things you don't want to do without the solid use case, right? Because otherwise you'll build a beautiful contraption and it will be good for nothing.
yeah,
All right. Thank you, Thomas. That got me thinking. So yeah, I'll go back to the thinking and probably slide into the weekend that way. So
yeah.
I hope you do too.
So happy templative weekend, everyone,
Yeah.
and
Nice.
see you
Thank
soon.
you so much. Bye, Thomas.
Bye.
Bye, everyone.